Hello folks, we're here for the second part of the video presentation on passive solar. And now that we've reviewed the framework for better understanding the science behind some of the concepts that pertain to passively heating and cooling building structures, we're going to talk about the types of passive solar systems. Basically three passive solar systems that can be utilized in a building to heat or cool it. These are direct, indirect, and isolated gain systems. Starting with direct gain. Direct gain is the simplest application of utilizing solar energy. Much like how the interior of an automobile drastically heats up on a sunny day when the windows are rolled up and the vehicle is in direct sun, exemplifies how direct gain works. For direct gain to provide warmth after the sun is gone, sufficient thermal mass infrastructure is a requirement. Otherwise, the heat energy would not be stored and the rooms and buildings would just cool off. So with direct gain heating systems, the idea is to utilize the sun in the winter and block part of it during the hotter months. Typically a roof overhang is adjusted to block the sun in summer by calculating the necessary angle that sunlight will penetrate. In the winter, because the sun rises at a shallower angle, the roof overhang, based on the correct geometry, will fully let the sun enter the glazing and thus penetrate the interiors and thermal mass. So here to my right we have just a building structure, and we've got the higher summer sun, and you utilize roof overhang or shading. There's a number of ways to do it to block the sun during summer, and then wintertime we will be utilizing that angle of the sun, which is lower in the horizon, and it's going to penetrate through the glazing of the windows and heat up the thermal mass here. So as many of you know, the angles of the sun drastically change through the seasons from winter to summer. So here we've got the summer sun starting in the east and going at a much higher angle and dropping down to the west there. So that's broader and higher in the summer. Wintertime, the angles change, the sun drops, and it's not quite as broad there. So if you've got a spot at home where you can kind of study that difference in the summer versus the winter, it's pretty interesting how those angles are more drastic than you realize. So, okay, good enough on that one. So that's just touching on direct system there, and the angles of the sun from winter to summer. The next system is the indirect gain, and with an indirect gain system, there's a number of them, but typically we have something that's called a trombe wall, which is next to the glazing. So you've got the opening of the structure, and then you have this wall that um, is is a thermal mass, and it's right in line with the angle of the sun, and that sun will heat up this wall thermal mass, and there's a number of ways to to move that air through the house at times when you need the heat. So that's just an indirect gain system example. And there's isolated gains, which use convection to take hot air to a living space, or utilizing air pressure to move hot air and cool air into spaces that need cooling. So with the isolated gain system, you could use a greenhouse that is attached to the building, and you heat up that space, and then you move that air appropriately to areas that need it. And there's also more sophisticated isolated gains. I'm going to show an example here. So with this isolated gain system, it actually uses the cool air from the ground to cool the structure. And you see the air enters into a duct or a pipe, and using air pressure, the air is brought into the building, pulling cool air in and cooling the building. So after the type of passive solar system is determined for a building, specific strategies for the building that is best suited for its use and location must also be considered for an effective passive building design. So we went from systems of direct, indirect, and isolated, which can be utilized together independently, and then now we're moving into strategies, and those are building orientation, solar shade, thermal mass, glass type, ventilation, room management, putting your certain rooms and parts of the house that are ideal in terms of where your heating and cooling is coming from, and daylighting, using the sun to naturally light. These are all strategies. They're all important characteristics of building design that can best aid in utilizing passive solar energy. A thorough discussion of these strategies is beyond the scope of this presentation. However, we'll touch on one strategy, building orientation, which is fundamentally critical for passive solar. Historical records indicate indigenous people understood well the importance of building orientation and utilizing passive solar energy. Despite not having such modern materials of glass, concrete, etc., they're still able to take advantage of it. And the Anzadi Native Americans built their homes in the side of cliffs in what is now known as the Colorado Plateau, Utah, Colorado, Arizona, New Mexico, those areas. These south-facing buildings were placed within the side of the cliff to avoid the sun in the summer, but make use of the sun during the winter. So it's interesting how they were able to take advantage of passive solar energy and utilize that within their building structures without having modern materials. This is one of the cliff dwellings that is common in that area of the U.S. So moving on, we're going to stay on the building orientation for a bit. Appropriate orientation of the building is the most fundamental and generally most easily addressed aspect of passive solar design. It's a good starting point, if you will. We're going to briefly look at a study that, or talk about a study that conducted modeling experiments to assess the orientation of a building and its effect on energy efficiency. Using computer modeling of existing residential house designs, the study sought to reveal what designs were most adaptable to orientation, improving thermal efficiency. The study revealed how orientation affected passive solar benefits across a wide range of standard building designs. The modeling analysis of these designs showed a wide range of performances across building size and suggested that house size is a critical factor in performance. The study supported the conclusion that passive solar energy efficient design can provide an important and low cost step towards reducing environmental impacts. Also, the study made note that building regulation could be used to further drive energy efficiency standards in terms of monitoring or regulating building orientation to improve energy efficiencies. So that particular study used computer modeling to review all these designs and orientate a building model to see how the orientation changed energy efficiency, and that brings us into a discussion of computer modeling, which is it's a pragmatic solution for implementation of passive solar designs. So let's touch on a few things that computer modeling allows us to do. So to help improve passive solar being adopted in the building industry and make overall gains in adaptability for new construction and existing structures, computer technologies utilizing modeling as a pragmatic approach here. Using computer modeling is advantageous in that it can create better designs, improve existing designs, and substantially save costs and time. There are two practical reasons for turning to computers as an aid in environmental design. They can save the designer effort and time, and they can offer the opportunity to work with more information, more complete information about the effects of design decisions. And so there's a lot of trial and error with this, and if we can model it on a screen and with software, that saves a tremendous amount of effort, resources, etc., versus actually trying to do it out in the field or creating physical models as they've done in the past. So also, these features of modeling may help with increasing the commonality of passive solar in the building marketplace. So moving forward, if we can develop software, or it's actually being developed, that'll take standard existing designs that are already being built, where the efficiency is already there for building these type of structures. We can use that modeling to give us an idea of how passive solar systems and strategies are going to affect energy efficiency parameters. For example, the last example where the study did that, and it just orientated already existing structures in these modeling programs to see how these parameters were potentially changed. So some current technologies of computer modeling include the ability to showcase how sunlight moves across the building and throughout building rooms, considering the latitude of the building, time of the year, and other geographical features. So here is a animation showing some of those things, showing how modeling how the sun is going to affect the building structure. So let's take a look at this. As the Earth moves through its annual season, smart design allows the home to take advantage of these things. Notice how the sun is blocked by the roof overhangs. And this is the interior of the house. We see the angles of the sun coming in during the time of the day and where it's at. So the overhangs are designed to allow maximum light of the heat in the home. Here's the modeling in the winter showing how the sun is going to hit the building and where. And also give us a winter depiction for the interior where the sun's going to be at. So we can check design ideas and engineer appropriately off of these modeling technologies.
Passive Solar Simplified, Part 4 by Thomas Dewar.
So that wraps everything up for Part 2. In the video, we went over systems, strategies, and discussed the importance of computer modeling for pragmatic approaches for implementing passive solar design. The next part 3, we're going to be talking about moving into the sustainability of passive solar systems. Thanks.